Thanks for coming back. So now, please complain if this chalk is not good. Go back. OK.
So it was very easy.
It was pretty quick.
It was quick. So you take the other one.
So I promised level 2, right, to go from dimension 1 to dimension 2. But there's a stepping stone, which is to stay at level 1, but do something more geometric. So I call this level 1 prime. And so the idea is the following. Now we can take K is FQ, let's say FQ bar. But at some point, it's good to remember that this FQ bar comes from FQ, and everything will have an FQ structure. Or we could also work directly from C and lose a little bit, but not too much. So the idea is that this orbifold that I considered before, MQD of FQ, is the groupoid of FQ points of a stack, of an Artin stack that I call MQD. Okay, so now it's really a geometric object. And which is what? Which is just, let's look at this. The direct sum for all edges in my quiver. So E was the set of edges, if you remember. And then I have, well, let's write like this. Well, OK, now let's write hom K to the D starting of E, K to the D end of E. Yep, and then I quotient by the product over all I of GLDI of K. Okay, here maybe I'm just writing the set of points, GLD. Yeah. So this is a quotient stack, and I will just need it actually work with a C or FQ bar. But this is a global quotient stack, so it's a smooth global quotient. Okay, and so we can use the Fizeau function correspondence. Fizeau function correspondence, and when we're going to replace this algebra of functions over the FQ points by actually, say, a category of, or maybe a subcategory of constructible sheaves on these stacks. MQ, let me just say MQ. And we just take QL bar coefficient. OK, if we want to keep working with FQ bar, let's just take QL bar. OK, and then we want to lift all structures to this setup. OK, so why you would like to do something like this? Maybe it's not completely clear from the start. But at least you can imagine that you will get more structure by looking at sheaves rather than just looking at dimension of the stalks of these sheaves. And in here, we know that there are some special heart, the perverse sheaves, and some special basis, some special simple objects, which are the simple objects in these in this heart, which are the simple perverse sheaves. And maybe when we consider what these are, and we go back to this setup, we get some interesting functions. Okay, so that's kind of a general phenomenon that whenever we can lift something from functions on some set of FQ points of a stack, then we should try to consider constructible sheaves on the stack itself. Okay. So the first thing that I want to say is that this diagram, we can really now make a diagram of stacks. Everything is a smooth stack. M Q D1 plus D2. This is P, and this is Q. And this is a diagram of smooth stacks. So let me say some properties of these. Well, first of all, you can, well, this is defined as a stack parameterizing short exact sequences, but you can identify it with the total space of a certain complex over this pair of stacks. So imagine that I have 2 points here over some scheme, test scheme. And so what I want to, the fiber of this, as we said, is some x1 divided by hom. That would be the automorphism group, extra automorphism group that we would get. So this map is not going to be representable, and it's going to be the total space, right, like this, of this R hom over Q between the tautological so where R hom, where ED, this is, let's just write like this. This is a coherent sheaf over MQD cross I is the tautological vector bundle. Okay, but it's more than just a vector bundle. You also have a bunch of arrows, right, between these vector bundles corresponding to the quiver. So this is just like over a surface. You have the moduli space of coherent sheaves on the surface, the moduli stack of coherent sheaves on the surface. You have a universal sheaf. Here, this is the universal sheaf, but it's the universal representation of the quiver. Okay.
What's the shift?
By 1.
It's
1, yes. So it is 1 because I want that in degree 0. When I take the cohomology, I have x1.
okay.
And then in degree 1, which is the automorphism, I want the hom. Yep. Right, so x2 is 0, but I want x1 divided by hom. Okay, so since my category rep Q is of homological dimension 1, this complex R hom E1, ED1, ED2 shifted by 1 is of perfect amplitude zero, 1. And so this is, so Q is what is called a stack vector bundle. Which I mean the following. So you have MQD1, MQD2, and over this I have a complex. Let's just call it E. Right, which is this E minus 1 goes to E0. Okay, it's just a complex. And these are vector bundles. Okay, these are vector bundles let's call this map F. These are not the tautological bundle, right? This is rather these vector bundle. This is a presentation that you can write explicitly for quivers, very simply. This is a presentation for this complex. Okay, this is representative of this complex in the derived category of perfect complexes on MQD1 cross MQD2. And what we have is that, so the kernel, so what I'm looking at is E0 quotient by E minus 1. Okay, the total space looks like this stack quotient over MQD1 cross MQD2. Okay, I can take the total space of E0, that's just a vector bundle over that, and I have the total space of E minus 1, and there's an action of the total space of E minus 1 on E just by F and addition, and I take the quotient stack. Okay, and this is what this mxt is. Okay, so this is a stack vector bundle of rank, the Euler form, the non-symmetrized Euler form, D1, D2. This is maybe non-symmetrized. Okay, Euler form. Okay, so this is the map Q. So it's very nice. It's a smooth map. It's almost like a vector bundle, except that it's not representable. Okay, so the dimension of the fiber may jump, but whenever the dimension of the fiber jumps, the dimension of the stabilizer, which is a unipotent group, jumps by this amount that compensates.
Sorry, the Q is the map on the right.
Q, yes, yes. Yep. Yep. This is Q. Okay, and then if I look at P now, the fiber of P, and I look at the fiber of a point N, then this is actually the quad scheme. Let's say quad scheme of D one-dimensional quotients of N, and from this we get that P is proper. So we are in the situation where this map Q now, an actual map of smooth stacks. This one is very nice. It's almost like an affine fibration, except it's not representable. Okay, it's a stack vector bundle. And this one is a proper morphism whose fibers are more interesting, let's say. Okay, they are Grassmannians. And so they, yeah. In general, singular projective manifolds. Okay. So now what we could do, but we don't want to do it, we could just consider the collection of derived categories of constructible sheaves on all these stacks, MQD. Okay, and we could equip it with a functor which would be Q upper star or upper shriek, P lower star. Okay, and that would give us a very, very large category, all constructible sheaves on these stacks, and some operations on that. But that's just going to be too big. I don't really know the meaning of that. And so instead, following Lustig, I should have said that level 1 prime is essentially all due to Lustig. During the 5 years he worked on the topic and then did all that. So consider the subcategory. Let's call it QQ inside dB constructible sheaves of MQ. Okay, this is just a union over all D of MQD. So we consider the category generated in the precise sense by the constant sheaves. Let me write Q L bar in M alpha I. Okay. So we mimic the construction of the spherical Hall algebra. We consider some specific objects, the constant sheaves, on the stack of representations of dimension alpha I. So most of the time, this is just point mod GM. Okay, so I'm looking at GM equivariant perverse sheaves, but I don't keep the GM equivariant structure. It's just a constant sheaf. And so I have these guys, okay, and then I see whatever they generate. So it should be and stable under. This is what I mean by generated. So shift direct sum, direct summons. And, of course, the operator of multiplication, which we called int, which is just p lowest star, q lowest upper star. Okay. There's not much difference between q upper star and q upper shriek, because this is just an affine vibration. Let's just keep it like that. Okay. So this is really the analog of the spherical Hall algebra. Okay, just start with some family of simple, easy constructible complexes, and then I see whatever I generate. There's one operation that you should respect. You have to respect this operation, okay, because it's something non-trivial that you're doing. You're starting from a collection of these very simple constructible complexes. Then you iterate the multiplication if you want, and then you get some large complex. And actually, because Q is smooth and P is proper, and these are all, these are simple. They're shifts maybe of some simple perverse sheaf. What we always get is a semi-simple complex, a direct sum of shifts of perverse sheaves. Simple perverse sheaves. Okay, this is what we would naturally get, but now I'm saying in this category I also throw in all the direct summons of these semi-simple complexes. Maybe I have to write it. So note, as Q is smooth, P is proper. The decomposition theorem that I think Junliang must have mentioned yesterday implies, let me write, decomposition theorem implies that, let's say, let me write iterated int, okay, int of, and let me write Q L M alpha I1. So I look at all the possible monomials that I can get. Alpha IS is a semi-simple complex, which is a direct sum of shifts of simple perverse sheaves. And in this category, so QQ contains all direct factors appearing this way. Okay, so that's where you need some respect, because this is something that does not make any sense for functions, right? If I have a function on some set, it does not make sense to decompose it into a direct sum of functions. Okay, but if I have sheaves, I can actually decompose into a direct sum of sheaves, and I can take each of those.
Yes. Nowadays, is there some more direct way to realize the QQ as some function from category stacks to G categories and so on, instead of going via all these detours?
Instead of saying it is the category generated by all these guys.
Yeah. There's some.
So, I mean, you can translate this into saying that you have a bunch of diagrams, iterated diagrams, and you look at the image of the constant sheaves under all of these.
Yeah, but then how you incorporated taking the direct sum
and then you have to take the direct sum out of that.
So you're not aware if someone work out some intrinsic way to define this category.
Yeah, no. Okay, so let me give a name. Let me give a name. Oof. Okay, so PD is going to be the set of P simple perverse sheaf P is in QD. Okay, all the simple perverse sheaves that arise. And then I'm going to look at something that you could call the graded Grothendieck group of this category. By the way, somebody complained that there were too many Q's.
Yeah,
I'm sorry. This is Lustig's notation. I don't dare to modify it. Yeah, and this is PD, okay? And this is, by definition, the direct sum over all D and P in PD of, let's just denote it like this, BP, just a symbol, V minus 1. So you should think that this looks like the Grothendieck group, except that in the Grothendieck group I would have to put V equals, say, minus 1. Okay, so this thing here, so BP V to the L corresponds to B of, let's say, P shifted by L. Okay, if you want to view it as a Grothendieck group, you should say that, okay, it is a Grothendieck group, but whenever I shift, I don't multiply by minus 1, I multiply by V. Okay, so it's like V version of the Grothendieck group. And now I have a multiplication from K to K has an algebra structure, associative algebra. So how do you define such an algebra structure? You take two elements in here, say BP1 and BP2, and then I look at the induction product of P1 and P2. What I get is a semi-simple complex, which is a direct sum of shifts of simple perverse sheaves, and then I just keep track of the shifts and multiplicity as a polynomial in V minus 1. Okay, maybe I'll just write that. Let's say.
Sorry.
Yep.
When you fix D and you look at the decomposition theorem of the mapping, can you determine the supports explicitly or you just...
Tough question. So for certain quivers, we know what the support is precisely. For certain quivers, we can classify all of these. Finite type quivers, we can do it. Affine quivers, we can do it. In some other cases, you should ask Lucien about it. Totally negative quivers, he can do it. In general, no. There's a conjecture, beautiful conjecture, that I will maybe state, now that you're asking the question, which gives some kind of geometric characterization of the perverse sheaves that arise in terms of their singular support. But yeah. Okay, so in associative algebra structure, maybe I'll just write it like this. BP times B, let me not use PQ again, it's okay. P prime is the direct sum of B P double prime times, how do I write this? Sum v to the I dimension of Ri hom p double prime induction of p prime. Okay. I'm making it look very complicated. It just means that, you know, when I have an induction product of two of these perverse sheaves, I can just keep track of the multiplicity and the shift of their induction product and write it in terms of simple perverse sheaves. Okay. All right, so this is an associative algebra question.
So the P bracket L is just the shift by L?
Just the shift of P by L. I'm just keeping track of that. And so over FQ bar, over FQ, you could do something smarter. You could do something seemingly smarter, which is take the trace of the Frobenius in this multiplicity space. Not just the dimension of the stalk, but the trace of the Frobenius. That would be more natural. Turns out that they are the same, but this is a deep theorem of Lustig. But maybe I mention this only later. Okay, and now something that will seem very natural and correspond more to the spherical whole algebra. Let's take K prime as the subalgebra inside of K, generated by, let's say, B QL bar M alpha I. I in I. Okay, so now I'm taking these. So maybe let me recap again quickly. I constructed a big category where I started with simple objects. Then I do all the possible products, and I take all the direct summands. I get something that could be out of control in principle, because I split all these semi-simple complexes and I look at the direct summands. Okay, and then I built, by standard process, I built an algebra out of that. Okay, which is a module over z vv minus 1, actually, integral. Okay, but now what I can do is I can, okay, I did not like, after all, this taking direct summands, and I want something simpler. Then I can just take the subalgebra generated by the simple object. Okay, by these very specific simple object. So now I can state the theorem. Okay, let me use another. So I think this is really beautiful theorem by Lustig. So first of all, K equals K prime. Surprise. So what does this mean? It means that, in fact, any direct summand, I could obtain as a linear combination, a virtual, in fact, Z linear combination, or ZVV minus 1 linear combination of these monomials. Okay, so these semi-simple complexes, in some sense, they do not just generate it after I take direct summands. They actually generate it on the nose. Okay, so that's really nice. Then, second of all, so there exists a coproduct. So in the FQ story, the product and the coproduct were kind of easy to get one from the other. Here I would say you need something slightly more refined called hyperbolic localization, but it's still okay. So there exists a coproduct. Let's call it res. Not so obvious is that it preserves this subcategory. Okay. Q2. Okay. So defined using what's called hyperbolic localization. I'm going to put that on Lucien's head. If you need something, you can ask him. So, yeah, it is a variation of what you would get when you run the diagram the opposite way, except that you have to do it using the correct combination of Schwick and star. So that's 2 and 3. There exists a bialgebra isomorphism. So again, twist it. Between u v square, just to make Francesco happy, and k prime, therefore equals k, which maps EI maybe to be the IC sheaf, so maybe something like v minus 1 QL bar M alpha I. Okay, so.
You mean a B of that thing?
Sorry? B, thank you. B. So v minus 1 B of that thing. Yeah. Okay, what's the corollary? I have to speed a little bit, but what's the corollary? And this is why Lustig wanted to do that. The corollary is that, okay, K prime in principle was just an algebra that had somehow not so much to do with perverse sheaves because it was a subalgebra inside an algebra obtained by, generated by simple perverse sheaves. Now, because of this, they are the same. So I can take the simple perverse sheaves and look at their corresponding element by this isomorphism. And I get a basis. Okay, so corollary. Let's call this psi. The set of psi minus 1 of BP, P in P, is the so-called canonical basis of uv square n. Okay, so, and this canonical basis has some beautiful properties, but that's, I'm not going to talk about it. And by the way, I forgot to say, but there is a coproduct plus a pairing, adjoint to int with respect to a pairing to dbvec, which is kind of a standard pairing PQ. I map to the compactly supported cohomology of dp tensor Q. Okay, let's not worry. There's a lift of the orbifold scalar product. Okay, so maybe idea of a proof. Very vague idea of a proof. So 3, so maybe 2. 2 is this coproduct. The fact that it preserves this category is not obvious. Okay. And so it comes from a stratification of what? You consider this mx d1, d2, and then this goes to m d1 plus d2, and then you decompose d1 plus d2 into two other ways, into another way, d prime 1, d prime 2. So what does this statement say? It says that this is obtained by some induction. Okay, this is an induction, and then I apply some coproduct to that induction. This is a product, something that comes from a product. I want to apply a coproduct to that. So I want to decompose the operation product, coproduct, into a bunch of operations which are coproduct, product. Okay, and when you do this from starting from dimension 1, then you will get exactly that it is preserved on the just products. Okay, so in order to do that, you need to understand this kind of stratification, a stratification of this kind of fiber product, which is so fiber here is the set of filtrations of a certain type of my object. This is filtration of another type of this object. Okay, and one filtration will encode the extension, and the other filtration will encode the restriction, the coproduct. And so I have to understand how they compare with each other, how they intersect. Okay, and this is stratification in terms of something like Brugha cells. And one can show that all these Brugha cells, they have some nice purity property. And out of that, you can actually perform the computation and show that you remain inside this category. Okay, then 3. Again, it follows from non-degeneracy of the pairing. Okay. And then I want to say a few words about 1, which is the most interesting one. So just a few words, because so I do have 20 more minutes, is that right?
23.
23 minutes, okay.
It's really change
Everything, yeah. So 1. Okay. So we need to show that each simple guy is actually a virtual linear combination of products like that. Induction QL bar M alpha I1 QL bar M alpha IS. Okay, we need to show something like that. Okay, by definition, by construction, P arises as a direct summand of some, let's call this L for Lustig, and next time L for Le Mans, let's call this L for Lustig for the moment, I1 IS. Okay, so it arises as a direct summand of some Li1 IS. Okay, by definition, this is a simple perverse sheaf, a direct sum of one of these guys. Okay, now let's assume that IS is a source of Q. Okay, at some point we have to use the quiver, right? So what do I mean by source? I mean that this is the vertex IS, and the arrows just all leave this vertex. So no arrows go inside. Now, if you think about it, or another way of saying it is that x1 from Si to Sj is equal to 0, sorry, Is, SIS is equal to 0 for any I. Okay, so now imagine that. So what can we say about P? P arises as this product. This product, by definition, counts the number of filtrations of an object such that the successive factors are of dimension alpha is up to alpha I1. Okay, so anything in the support of P, in the support of this thing, will have a sub-representation isomorphic to this one. Okay, dimension 1 at vertex is. Okay, but now if you think about it, this has to split as a direct factor because there are no maps that could hit this representation anymore. Right? So any M in the support of L I1 up to IS has SIS as a direct summand. Okay, this is because this is a source. Okay, so this means that we can stratify the set of representations of dimension D according to, let's say, M D I S. Let's just use Nustic notation. IS L. Okay, L bigger or equal to 0. And this is what? This is the set of M such that M is isomorphic to S IS L times plus M prime. Okay, and this is the maximal number. So all the others are different. All the other simple indecomposable factors are different from this simple object. Okay, and then we have that the support of our simple perverse sheaf P, of course, is included in the support of L. And this is included in the direct sum for L bigger than 0, strictly bigger than 0, of MD ISL. Okay? All right. And now, moreover, let's moreover, one can easily show that MD ISL, I can take the quotient. So this subobject, maximal subobject, is canonical. No. The other factor is canonical. And so I can take the quotient by that. And so this becomes a nice isomorphism, maybe up to some affine fibration, I don't remember exactly, with M D minus L alpha IS 0. Okay, and then one can use that to, one can leverage this to prove by induction that P is in, let's say, induction of Q, and then let's say D minus L alpha IS Q L alpha IS. Okay, and maybe I have to be a little bit careful. This is the sum for L prime bigger or equal to L. Anyway, you can find this in some original papers of Lustig, or I wrote a long time ago some notes where this argument is is given in detail, but the point I want to make is when our simple perverse sheaf arises as a direct summand of a specific Lustig sheaf, right? Specific in the sense that the last term, is, should be a source of the quiver. Okay, in this case, we can perform some induction because geometrically we understand well what's going on. Okay.
What happens if there are no sources?
Ah, okay. And this is, you're right, it's not finished. It's not finished, not at all. So you're right, maybe there are no source. And so the ingredient, so in order to put ourselves in this situation, and this is the other idea of Lustig, we use some Fourier transform. Okay, so what's the main observation? Is that suppose I have Q is I, and let me write, say, E prime union a certain edge E. Okay, and let me write Q star is a vertex where I instead use the dual edge. Okay, so if E goes from I to J, then E dual goes from J to I. So I reverse the orientation of one arrow.
And you can iterate in order to create a source.
Yep. And then I have to relate these different algebras. Right? So first of all, the stacks themselves, you can show that MQD, this goes to M, so IE prime, and MQ star D. Okay, and these are dual vector bundles. Okay, reversing one arrow geometrically means that you're replacing a hum from Vi to Vj by a hum from Vj to Vi. This is just a dual vector bundle. And now I have a Fourier transform functor between derived category of constructible sheaves on this one and derived category of constructible sheaves on this one. And then you show that these whole categories, so this Fourier transform, MQD MQ star D is restricts to Q and is an isomorphism for, let me just be a bit vague, Q, this category is Q, and also this K, okay, KQ. So we iterate this, and then we can assume that we are over source. Sorry? What happens if my quiver has a loop? Okay, let me remember. Yes, what happens if a quiver has a loop? You have to do more work, and this work was done by Tristan Bozek. You're right. Here I kind of, yeah.
Does this argument also say that the points are independent of the orientation?
Yep.
And this is the proof, like otherwise it's not true. Like if you can say it's
So, yeah, so, okay, the entire whole algebra. I would need to relate the entire whole algebra to something like this. This would be too small a category. I would need a larger category. So actually, I still think using Katz's polynomial is going to be the best. Okay. So one offshot that I want to say, and this would now lead me to this dimension 2 world. So what's the moral? what do we learn from this complicated proof? We learn that it's best to consider all orientations at the same time. Okay, so we should think that we have a bunch of categories for every orientation. So for any orientation, let's call it E, we get a category Q, okay, I, E, okay. And then we have all these equivalences, this Fourier transforms. And so we could say, okay, maybe that's the right object. We consider all these categories for all orientations, and we have the Fourier transforms. And then maybe we have to be careful about signs when you start composing these Fourier transforms. But okay, but in fact, it's better to work directly on the cotangent bundle to MQ. Okay, this one is independent of E directly. Okay, so instead of saying, okay, sometimes I need this vector space E, sometimes I need this dual, I just take both of them. Okay, that's my attempt to motivate passing from dimension 1 to dimension 2. Okay, so that in this proof of an important, beautiful theorem, we kind of consider all these categories at the same time, and maybe it's better to just accept the fact that a quiver should not come with a preferred orientation. All right. So now I just have a bit less than 10 minutes. Let me just say, let me just quote general principle. So if X is smooth, scheme, but stack also, then you have this characteristic cycle map. So it goes from the Grothendieck group, the actual Grothendieck group, not the graded Grothendieck group, of constructible sheaves on X, say with Q coefficients, and X is smooth over C. To some cycles, Lagrangian cycles. Let me write Lagrangian GM equivariant cycles on T star X. So this is some kind of, yes, it's some kind of direct limit of, say, Borel-Mu homology of Lagrangian cycles in T star of X. Okay, and limit over the union, I mean, for the inclusion. So let's just say Lagrangian cycles. Okay, so satisfying some properties that give you an idea of what this beast is. So first of all, when I apply to a local system, this is, say, -1 times the dimension of X, the rank of this local system, times the class of the zero section. Okay, this is the zero section in T star X. So there's a sign, and then essentially it's just a zero. So if you take a rank 1 local system on X, okay, this is a local system, a Lis sheaf. If you take a rank 1 local system, then you just get the zero section. Okay, should be a local system on the whole of X, right? Not the intermediate extension of a local system on even an open subset of X. Okay, then if you have a triangle, so yes, if you have a triangle, it's additive on triangle. Let me say additive on triangles, distinguished triangles. And maybe just say in general, the characteristic cycle of complex P, maybe simple perverse sheaf P if you want. You can consider that case. This is, when you project it down to X, it's in the support of P. P is the map from T star X to X. Okay, so in fact, what you end up having is you take a, say, for simplicity, let's take a perverse sheaf. Doesn't change much, but take a perverse sheaf. Then you know that it is locally constant along a certain stratification. And the characteristic cycle that you will get will be a linear combination of the class of the cotangent, how do you say that? Co-normal bundle to these various stratas with some coefficient which depends on the restriction of your perverse sheaf along these strata. Okay. So anyway, there is something like this with some nice property, functorial properties with respect to proper push forward, smooth pullback. So I guess let me just, so there are older references, but I think everything that you need is, you can find it in the paper by Lucien. Something about geometric realization of unipotent, nilpotent something. I don't remember. But anyway, if you want to have a quick introduction to this thing. So, all right, so I have 3 minutes. So let me just state the theorem in a vague form. So when I take X, so K equals C, when I look at the span, so first of all, for any D, there exists a Lagrangian substack lambda D inside the cotangent to MQD, which is called the Lustig Lagrangian. Okay, such that, okay, there exists, not a big theorem, but okay, you can actually describe exactly what it is. It's very nice. And then the characteristic cycle map is an isomorphism between the usual Grothendieck group, now not the graded one. So let me write like this. The graded Grothendieck group, we had K prime. No, K. K was the graded Grothendieck. Let me just write it. Of QQ. But here I put V equals -1. Okay. So I specialize it to V equals -1. And this is an isomorphism with the top homology of this Lagrangian lambda. Okay, so it's a very nice way to parameterize the simple objects here. Okay, at least to parameterize a basis in here by irreducible components of this Lustig Lagrangian. Okay, so what I'm saying is you have this category of semi-simple complexes or simple perverse sheaves. I mean, yeah, the set of simple perverse sheaves in the MQD. Then you take all their singular support or the characteristic cycles. Take all of them. And what you get is exactly the set of Lagrangian cycles supported on this, independently defined Lustig Lagrangian subvariety. And this is actually an isomorphism. Okay, so you can detect if you want, these various simple perverse sheaves by their singular support. Okay. All right, and now just as a teaser, I know everybody's hungry and tired, just as a teaser for tomorrow, let me just give more. So the sum of the dimension of h top lambda d z to the d is this exponential of the sum of Katz's polynomials evaluated at 0. That's not surprising. Okay, that's not surprising. It's some other form of Katz's conjecture. Okay, because we know that this guy here has the size given by the constant term of the Katz's polynomial, and we know that this is an isomorphism, so it's not surprising. But what is more surprising is that now I take the graded dimension of the entire homology of lambda d z to the d, then this is the platistic, then I recover the full Katz's polynomial t z to the d. Okay, so I can recover the entire Katz's polynomial purely geometrically by considering not just the top, so the irreducible components of the Lustig Lagrangian, but the entire cohomology of the Lustig Lagrangian. Okay, and then there exist algebra structures on everybody. On this one and this one. Okay, and this is the Coha. This is exactly what is called the Coha. Okay, so now we have kind of answered the question that I asked before by passing to the cotangent, and instead of looking at functions, we look at perverse sheaves, and then instead of looking at perverse sheaves, we look at their singular support. We have found a beautiful Lagrangian stack whose cohomology is exactly this Katz's polynomial, and which actually will have an algebra structure that contains, as its degree 0 part, if you want, the degree 0 part, the top part, this quantum group. Okay, so this I will talk about tomorrow.